I want to talk about the concept of complexity according to Richard Dawkins. I'm Eric Steinhardt, and you can learn more about me and my work at my website, www.ericsteinhardt.com. Let's talk about complexity. Things have varying degrees of complexity. Complexity is a property of the types of things and not particular things. And this is because one thing can be of many types. We focus on the complexities of types because, look at this, here's a particular thing. It falls under the type gorilla. Now the type gorilla is complex, but it also falls under the type material thing. And the type material thing is simple. Since one thing can fall under many different types, we have to talk about the complexities of the type. Complexity is going to be based on the idea of scrambling the parts of types. Simple types are preserved by scrambling their parts, whereas complex types are destroyed when scrambling their parts. This means that simple types are stable when scrambled, while complex types are unstable or fragile when scrambled. Consider a swimming pool. If you scramble all the water in the swimming pool, you still end up with the type swimming pool. So the type swimming pool is simple. Consider an airliner. If you scramble the parts of an airliner, you almost always end up with junk. Scrambling destroys the type airliner. So the type airliner is fragile when scrambled, and the type airliner is complex. But we need to make the idea of complexity more precise. Dawkins just treats it intuitively and gives some hints about how to make it more mathematically precise. So we're going to use 7 steps, and here are the 7 steps of defining complexity precisely. First, we break the thing down into its parts. Second, we list all the arbitrary ways of reassembling those parts. Third, we list all the ways that recover the original type. Since they recover the original type, these ways are stable with respect to that type. Fourth, we count the number of arbitrary ways of reassembling. And fifth, we count the number of stable ways of reassembling, the ways that recover the type. 6, we divide the arbitrary ways by the stable ways, and then 7, we're going to take the base 2 logarithm to turn complexity into bits. Here are the 7 steps. So step 1 is going to be the breakdown. We start with some whole composed of parts. Look at the word CAT, and here I used Scrabble tiles. The little Scrabble point numbers don't mean anything, but they just remind us that there are 3 tiles stuck together to make the word CAT, cat. Let's break it down into its component parts, which are letters, the letters A, C, and T. Step 2 is we look at all the arbitrary ways to scramble those letters. We list all the possible ways to scramble the parts in our breakdown, and these are the arbitrary scrambles. There they are. One of these scrambles has 3 separate letters. 3 of the scrambles combine 2 of the letters and leave 1 off to the side. And 6 of those scrambles are ways of combining all 3 letters into words. Step 3, we look at the stable scrambles. We list all the scrambles that preserve the original type. Since they preserve that original type, the type is stable through those scrambles, and these are the stable scrambles. You can see with the red circle that one of these 10 scrambles is stable. Only one way of scrambling the parts reproduces the type CAT. Step 4, we find the arbitrary multiplicity. That is, we count the number of arbitrary scrambles, and this number is the arbitrary multiplicity. There are 10 arbitrary scrambles of cat, so the arbitrary multiplicity is 10. Step 5, we find the stable multiplicity. That is, we count the stable scrambles. There's 1 stable scramble of cat, and so the stable multiplicity is 1. There it is in the red circle, just 1. Step 6, we find the raw complexity of the type. And the raw complexity is the arbitrary multiplicity divided by the stable multiplicity. And that gives you the stability of the type. The raw complexity of cat is 10, right? 10 arbitrary ways of reassembling its letters divided by 1, one stable way, and 10 divided by 1 is 10. Step 7, we're going to get the complexity itself. There are two problems with the raw complexity. Raw complexities often turn into very large numbers very quickly, and 2, complexity is usually measured in terms of bits of information. Since bits are binary digits, and there are 2 binary digits, 0 and 1, we convert a number to bits by taking the base 2 logarithm. Thus, the complexity of a type is going to be log 2, that is the base 2 logarithm of its arbitrary multiplicity divided by its stable multiplicity. Here we go. What is the complexity of cat? The raw complexity of the word cat is 10. If we take the log 2 logarithm of this, logarithm base 2 of 10, we get 3.01 bits, and that's the complexity of the word cat. Let's continue with a couple more examples. Let's apply the 7 steps to the type rock. There's a rock. Step 1, the breakdown. We hit the rock with a hammer, breaking it down into some component parts. Step 2, we find the arbitrary scrambles. We list all possible ways to assemble the parts in the breakdown into a whole or wholes of any type. Take some glue to assemble the rock parts in any way you like into a new whole or many new wholes. These are going to be the arbitrary scrambles of the rock parts. This list of arbitrary scrambles will be very large. But step 3, let's find the stable scrambles. List all the scrambles that preserve the original type. These are the ways of assembling the rock parts into a rock or rocks. Since they preserve the original type rock, the type is stable through these scrambles, and these are going to be the stable scrambles. Any way of gluing the parts of a rock back together makes a rock or else many smaller rocks. So every way of putting the parts of a rock back together after hitting it with a hammer is a stable scramble. The list of stable scrambles is the same size as the list of arbitrary scrambles. Every scramble recovers the type rock, so the type rock is easy to recover. Step 4, find the arbitrary multiplicity. That's the number of the arbitrary scrambles. Let's just say there are 10,000 arbitrary scrambles, so the arbitrary multiplicity of the type rock is 10,000. Step 5, the stable multiplicity. Every way of reassembling the rock parts makes a rock or a set of rocks. So every arbitrary way preserves the type rock. This means that every arbitrary scramble is a stable scramble. So the number of stable scrambles equals the number of arbitrary scrambles. So the stable multiplicity, which is the number of the stable scrambles, is also 10,000. Step 6, we find the raw complexity. We just divide the arbitrary multiplicity by the stable multiplicity. That's 10,000 divided by 10,000, and that means the raw complexity of a rock is just 1. Step 7, we take the base 2 logarithm to find the complexity. The complexity is the base 2 logarithm of the arbitrary multiplicity divided by the stable multiplicity. That's just going to be the base 2 logarithm of 1, and the logarithm of 1 is 0. So the complexity of a rock is 0 bits. The rock has 0 complexity. It's a simple kind. And this makes sense to say the rock has 0 complexity. Hammering the rock just made smaller rocks. So you didn't alter the type at all. To get any complexity out of a rock, you'd have to break it down into its atoms, which then could be assembled into different types, new types. Let's look at another case, a bicycle. Look at all those different parts of a bicycle. Step 1, we break it down. Here we start with a bicycle and take it apart with some tools like a screwdriver or wrench. We break it down into its mechanical components. Step 2, arbitrary scrambles. We list all the possible ways to assemble the parts in the breakdown. You can use some glue or some tools to assemble the bicycle parts in any way you like into one new hole or many new holes. You could weld a wheel to the frame. You could glue the brakes and the chain together. These are the arbitrary scrambles of the bicycle parts. The list of arbitrary scrambles will be very large. Step 3, the stable scrambles. List all the scrambles that preserve the original type, the ways to assemble, the bicycle parts into a bicycle. Since they preserve the original type bicycle, the type is stable through these scrambles, and these are the stable scrambles. Very few ways of assembling the bike parts make a bike. Most of the ways of assembling those parts make junk. Now there's going to be more than one way to stably assemble the parts because, for instance, you could put the chain back together in many ways. A chain is a series of links. Chain doesn't really care what order those links are assembled in. If you've got a bunch of ball bearings that go into, say, the back wheel, well, the order in which you put those ball bearings into the wheel hub doesn't make any difference. Spokes, again, they're interchangeable, they're copies. The order in which you use the spokes to, let's say, put the back wheel together again doesn't matter. And it probably doesn't matter if you switch the rear or front wheel rims. Those are going to be the same. So the list of stable scrambles still is going to be much smaller than the list of arbitrary scrambles because very few scrambles recover the type. There's going to be a lot of ways to put those bike parts back together arbitrarily, but only few recover the type bicycle, and that type is hard to recover. Step 4, we count the arbitrary multiplicity, right? That's the number of arbitrary scrambles. We're going to just say again for comparison that there are 10,000 of those. We count the stable multiplicity in step 5, and we're going to say very few ways of assembling the bike parts make a bike. Let's say only 10 ways of assembling those parts make a bike. So the stable multiplicity is only 10. We get the raw complexity by dividing the arbitrary multiplicity by the stable multiplicity. 10,000 divided by 10 is 1,000. That's the raw complexity. We take the base 2 logarithm. The complexity of a bicycle is the base 2 logarithm of 1,000, which is about almost 10 bits, 9.97 bits of information. For any type, okay, we've got to compare complexity and probability. For any type, suppose you pick one of its arbitrary scrambles at random. What's the probability that the arbitrary scramble recovers that type? Here, it's just the inverse. The recovery probability is the stable multiplicity divided by the arbitrary multiplicity. So the recovery probability of a type is the inverse of its raw complexity. There it is. Recovery probability equals 1 divided by the raw complexity. What's that math mean? It means if you use, let's apply it to a rock, if you use a random lottery to pick a rock scramble, what are the odds that you get a rock? The recovery probability for the type rock is 10,000 divided by 10,000, which is 1. Every recovery yields a rock. So the odds of getting a rock if you pick a random reassembly is going to be 1. You get a rock. Simple types have very high recovery probabilities. Simple types are likely to be produced by random lotteries, and simple types are likely to be produced by chance. That's what a random lottery is. So, if you have a random lottery in which you simply pick one way of reassembling a rock out of its smashed up parts, one way of scrambling the parts, every way, that way is guaranteed to produce a rock again, or some smaller rocks. It preserves the type rock. The type rock has no complexity at all. Any way you reassemble its parts, after hitting it with a hammer, you get a rock. What about the bicycle? If you use a random lottery to pick a bicycle scramble, what are the odds you get a bicycle? The recovery probability for bicycle is 10 divided by 10,000 in our example, which is 1 out of 1,000, which is pretty small. This shows that complex types have very low recovery probabilities. It's not likely if you just pick a reassembly or an arbitrary way of assembling the bicycle parts, it's not likely that you're going to get a bicycle. This means complex types are unlikely to be produced by random lotteries. Complex types are unlikely to be produced by chance. And so complex types are improbable. Simple types are probable, likely to be produced by chance. Complex types are improbable, not likely to be produced by chance. I'm Eric Steinhardt, and you can read more about me and my work at ericsteinhardt.com. Thanks.